start now. And good afternoon to all of you. And I welcome all of you for this is the third day of this training program on on glaciers and remote sensing. So today we will talk about. Are I am audible now?
Yes, sir,
Hello.
you are. Yes.
Okay. So today we will talk about the remote sensing of snow and ice. Until now, you had a couple of lectures which talk about uh, general trend, a general idea about climate change, overall idea about remote sensing, and then about the importance of cryosphere, which is and the global distribution of cryosphere. So today we will talk about principle which is used for snow and glacier studies. So, so the first of all, before going into the characteristics or spectral reflectors characteristic of snow and ice, which help us to understand various types of snow as well as oil, as well as ice. It is important for us to understand how it looks like, and we will try to address why it looks different than many other features. So this is a picture which you have seen earlier, but now I'm talking about quite different context. This is a snow which is fallen on the ground immediately after the fresh snowfall. This picture is taken. You can see here, snow is extremely white compared to the other land features, particularly vegetation on which the snow cover is lying. So snow is white in color. The color of the snow is significantly changes uh, up to certain extent as it goes through the process of change. That means once it is fallen onto the ground, it goes to it changes its various physical characteristic. That means it changes its liquid water content, it changes its density, it also changes its grain size as well as it reduces its thickness as it goes through the process of melting. So it becomes very patchy snow, and many times the contaminants which is present into the snowpack, they gets filtered out and comes on the patch, comes on the surface because of the filtering processes. Uh, so it is looks patchy and dirty snow, and this snow has slightly lower albedo or reflectance than a fresh snow. Um, then, if you really look in terms of ice, when the snow gets converted into the ice, we will look into that processes, how snow gets converted into ice. This is a completely transparent snow. That means, if you look into the snowpack, so it is ice pack which is completely transparent snow. When that is essentially because the trapped air between the two ice crystal is removed and that space is really close, then it is called ice. With density is significantly higher, and you can see it is a quite transparent ice, which it becomes. And if you really look into the glacier ice, when the huge patch of ice you can see there, how it looks like. It is generally looks like, if it is very clean, bluish in tone, you can see ice because of the scattering properties. But top of that, there will be a lot of dirt which is sitting onto the ice. So you can really see that some places it is bluish tone, some places it is blackish tone because of the dirt, and sometime also because of the melting process, it also looks in white in color. So they have a different color. But when you see the glacier, because ice is one thing and glacier is another thing. So the difference between the ice and glacier is a mass of ice which is slowly moving down the valley. But that mass of ice contains various other features. That means there's a lot of debris on the surface. You can see there are some debris on the surface. Then there are numerous landforms, crevasses are formed, and then there is snow on the surface. So it looks quite different than the pure snow or the way pure ice you will look like. What you can see are their optical characteristics of that, and that of the landform, which is a glacier, is a slightly different. So it is important for us to understand how snow looks like, how ice looks like, how dirty snow looks like, and how glaciers look like. So this is important for us to understand differences between that. And sometimes what really happens is there is a significant amount of contamination onto the glacier ice. So this is a glacier ice which is in Sikkim, and when significant amount of volcanic activity taken place into the Iceland, and there's a lot of ash or deposited on the snow, on the ice, creating very different color, and it can significantly enhance the melting of glaciers because of the reduction in the albedo of ice. So you can see that the glaciers can have a different um, characteristics. They look very differently, and because of that, they have a different albedo, and it can changes the melting characteristics. So that is where it is important to understand. So let us understand some of the differences, how we will differentiate between snow, ice, and glacier. So what it really means is snow is a porous and permeable aggregate of ice crystal. So it is a series of ice crystals, um, and that ice crystal are interconnected by air and water. So generally, if it is a dry ice, then there are small crystals are there, and in between there is air in it. And if it is a wet, then it is generally that space is occupied partially by the water. So generally, density of um, is is less than 400 kilogram per cubic meter. So what will be the density of water? Um, uh, so it is important to understand. So I will. Um, Anyone can answer that question by sending on chat box that what will be the density of water, because we are talking here about the density of snow, which is less than 400 kilogram per cubic meter. So when what really happens is because of the various processes, the interconnected air or water passages, because so you have crystals, and in between crystals there is a water, or there is air. When it squeezes out completely, and if that air is removed, most of the air is removed, and that process by which, because of the compaction, when the air is removed, that is called as a sealed off process, and or a close off process, and then ice is formed. And once the ice is formed, then its density is goes up significantly, up to 830 to 923 kilogram per cubic meter. Uh, and then what happens in nature in a high altitude region when the ice mass becomes a huge sufficiently large, then due to gravity and creeping because of the internal deformation, what really happens is creeping takes place and the glacier is formed. However, ice should be formed due to metamorphism and recrystallization of naturally fallen snow on the land of surface. And glaciers essentially have ice, snow, water, and debris. So ice is an integral part of it, but it also has the snow, it has water, and it has debris. But the essential characteristic is it should be moving ice. It cannot be stagnant ice. And if it is stagnant ice, then it is a completely different characteristic. And if it is associated with the glacier, then it is called dead ice mounts or something like that. So it is different than glacier. So the terminus of glacier is is really we have to realize it is a part of the moving ice. So that realization is really important, and it will help you for interpretation of this thing. So if you look into the typical density as snow goes through the process of metamorphism, then it is a fresh snow which has around, if it is fallen under the dry and calm condition, that means there is no wind, and the temperature is substantially below the 0 degrees Celsius. It is not the wet snowfall, or it is 0 degrees Celsius, then there will be wet snow will be falling. If it is a fresh snow and dry, and it is a environment is calm, it is not windy, then it can have a fresh snow will have 50 to 70 kilogram per meter cube of its density. If it is a damp snow, that means if it is falling under the condition where temperatures are close to the melting around 0 degrees Celsius, then it has a slightly higher uh, density, and it can be around 100 to 200 meter. So you must be wondering why densities are important, because you will realize as we go further, reflectance characteristics of snow is significantly influenced because of the density. So density of snow is very important, and that is a key parameter in understanding how much water is stored into the snowpack. So if is a settled snow, that means the fresh snowfall has taken place, and over a period of time, the change in a crystal size of fresh snowfall will take place. We will see that later on. And it over a period of time, because of compaction, it settles down and its density increases 200 to 300 kilogram per meter cube. Then what really happens is at the bottom of the snowpack, there's a significant amount of um, moisture and the temperature, because if you really look into that, ice is a bad conductor of heat, and because of that, the 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 bottom of snowpack is relatively warm, and there is some moisture on that, and because of that, it creates a certain amount of thermal gradient into the snowpack. We will look into that, and that creates the depth hoar. So that has a slightly higher density. Then wind pack, if it is really a very significant wind is taking place in that region, then also it can increase to 350 to 400 kilogram per meter cube. When the snow goes through the process of metamorphism and it is a transition between the snow and ice, then it is known as firn, and it has and also very wet snow and fur, which can have between 400 to 800 or 830 um, uh, uh, kilogram per meter cube. It can have a ice density, and when it completely gets converted into the ice, then it is the density varies from 830 to 923 23 kilograms. So that is how density keeps on changing as snow goes through the various processes as it has fallen onto the land. Moment it's fallen onto the land, it gets converted into snowpacks, and the snowpacks goes through the different changes, and as it goes through the different changes, it converts in density, and it can go from 50 to 70 to 830 to 920 kilogram per meter cube, depending upon the condition. So what is, once snow is deposited, what are the changes in a snowpack takes place? That is also very important to understand. So there are uh, four reasons by which snowpack goes through the its changes. So one important characteristic is water equivalent. So what is the water equivalent of snowpack? It changes over a period of time. Then its temperature is also causing. So if you really want to know what is the water equivalent of snowpack, you should know two fundamental characteristics of snowpack. One is the depth you should know, and you should know the density. If you have depth and density, then it is possible for you to get the water equivalent. Then what also happens is there is a temperature gradient inside the snowpack. And because of the temperature gradients, what it changes is, it changes its hardness, it changes its strength, and it changes in grain shape, and it also changes in grain size. All this thing, and the liquid water content will also change because of all this thing. And it is very important to understand how much is the liquid water content in the snowpack. So because of the temperature, there will be a change in various physical characteristics of snow, and these characteristics are hardness, strength, grain size, and grain shape. In addition to that, another important characteristic of snow is the albedo. And albedo is significantly affected because of certain characteristics of the snowpack. And these are impurities. That means how much is a clay content or black carbon, whatever way you want to say that, impurities or soil, which is on the snowpack, which is really reduces its albedo. The grain size can also significantly reduce the albedo, even though relationship is a square root relationship. But increase in grain size can also reduce the albedo of snowpack, and the liquid water content can also reduce the albedo of snowpack. So these are the interlinked parameters, and they influence various physical characteristics of snowpack. So it is important for us to understand some of these parameters are important, particularly hardness, strength, and grain shape. These are important for us to understand how avalanches, because it changes the strength of snow and can lead to the avalanches. Albedo, which is depending upon liquid water content, impurities, and grain size, uh, and influences the melt of snowfall, and the water equivalent is how much water is available if you want to do the hydrological analysis. So in that context, all parameters are important for us to understand and study the snow characteristics. So the basic idea, you know, that as snow has very low density, and as it goes through the process and gets converted into ice, there is a significant change in the physical characteristic of snow takes place. And the change, and that rapid change in various physical characteristic of snow is known as snow metamorphism. So with changes in grain size, shape, liquid water content, temperature and temperature gradient, all these things leads to densification of snow, and snow converts into ice, and the process is known as snow metamorphism. So let us understand some of the things why it really happens. So let us look into the temperature gradient, one of the key parameters which influences the change in gray size because of the temperature gradient inside the snowpack. So if you look into generally, atmospheric temperature in the middle of winter is substantially low, and it can go as low as minus 10, 15 degrees Celsius, 20 degrees Celsius, or wherever you are, depending upon geographical location and numerous other conditions. However, if it is a thick snowpack, bottom of snowpack is rarely at the same temperature where top of snowpack is there. If atmospheric temperature is minus 10 degrees Celsius, then first layer of snow could be around minus 6 degrees Celsius, then it is a minus 3 degrees Celsius, you can see here. And as you move down below the snowpack, the temperature of snow is significantly reduces. And when it comes to the interface between the land and snow, the temperature of snow is 0 degrees Celsius. And it is quite, and because of that, there's a temperature gradient inside the snowpack. And because of the temperature gradient, there is a change in the shape of, because of the transfer of free moisture takes place between bottom to top, leading towards the change in the shape of the snowpack will takes place because of the temperature gradient. So there is also change into the snowpack because of the diurnal variation in temperature. What it means is that it's quite possible that you can look here if you have around 1.5 meter thick snowpack, then there will be a daytime temperature will be substantially high. It is around 0 degrees Celsius, and then there will be a melt on the surface of snowpack. But remember, in the middle of winter, if there is a small melt is taking place in the surface of snowpack, that liquid water will not penetrate completely throughout the snowpack. It will penetrate up to certain level. In this case, it is penetrating only first 20-30 centimeters. And then what will happen is the snow which is melted here get converted into ice, and this creates the exothermic reaction, that energy is released, release in the process, that water is freezes, and so there is a temperature gradient, and then evening time again it freezes. Again the surface goes very low, and there is a temperature gradient is there. So there is a variation in diurnal temperature gradient, and creating a metamorphism processes which is a much stronger in active layer in this. So it's quite possible that many times when you see there, if this process is very routine and very strong, then top layer, the layer which we are talking here, can become a ice lens. That means the melting, freezing can generate the ice lens there. And if there is a fresh snowfall on it, this becomes a slippery ground for future, and it can create avalanches in downstream. So this is also important for us to understand how the diurnal variation in temperature and its influence on changes in snow characteristics are also very important. And this is the precisely idea. If you can see here is, if temperature at bottom of snowpack is much warmer, and if the temperature on the surface is very low, and if you go into the region such as Arctic, where temperature could be as low as minus 30 degrees Celsius, but bottom is at 0 degrees Celsius and much warmer. So this is the idea used in igloo. So this is one igloo. You can see here, you can crawl inside the igloo and comfortably stay inside during night when the outside temperature is minus 30, minus 40 degrees Celsius. You are comfortably at 0 degrees Celsius. Sometimes they could be very spacious and could be very. I stayed a couple of days inside the igloo when I was a student at McGill and working in Shefferville. Remember, it's not a fun. It is a hard life over there. But important question is, you can survive a night. And then when temperature is extreme, you can so that's the you must understand, these are some of the survival skills you need to develop if you want to go into the high cryosphere region. So key question is, now we have seen why does snow undergo metamorphism, and that is because close to if temperature is close to the melting point, then it becomes thermodynamically unstable, and it creates large surface to volume ratio. Therefore, large surface free energy is available, and it minimizes, and therefore it becomes rounded and compact, and it gets compacted to overlying layers. I think we will look some of the pictures so you will get the idea. So there are indeed various types of metamorphism. One is the two predominant. One is dry metamorphism. That means no liquid water present. Temperature is less than 0 degrees Celsius, and a solid state in equilibrium with vapor. And the wet snow is a liquid water presence, and temperature is equal to 0 degrees Celsius. So in a dry temperature, a dry metamorphism is essentially driven by the water vapor movement into the pores. Water movement, vapor movement is driven by vapor pressure gradient, and which is controlled by temperature, radius of curvature, and grain size. So we already know that many of you, saturation vapor pressure depends upon temperature, warmer area can hold more vapor than colder areas. Radius of curvature, how curvature, particular part of snow grain is increased, radius of curvature and increase the vapor density, and the grain size decreases. So decreased grain size increases radius of curvature and therefore increases the vapor density. So this is the idea when it start it going to take into transformation. So when you have a very fresh snowfall, it is extremely dendritic in pattern. If snow has fallen under calm condition and it is much more freezing temperature, that means substantially below the 0 degree Celsius, then you can have a beautiful picture like this, which is the snow, and it contains the 90% of air. When the snowfall is taken, it is a 90% of air and it has extremely high albedo. As the vapor pressure changes and it tries to shade the dendritic pattern and it is become a more granular ice, then it becomes firm and it really becomes circular when glacier ice is formed, that crystal change into the circular. So you have 50% of air when it is granular ice, 20 to 30% of air when it is firm, and it is less than 20% of air bubble when it is gets converted into the glacier ice. So that is how the metamorphic processes, and that is how snow gets converted into ice. So key question is how long it takes for us for snow to get converted on the glaciers, whether it is Greenland, whether it is Vostok, Antarctica, whether it is in Antarctica, or whether it is Greenland. Remember, so if you are in Greenland, then you have a depth at which snow or a fern get converted into ice is approximately 65 to 70 meters. And it takes approximately 100 years, and uh, the temperature, which is around minus 19 degrees Celsius, and accumulation rate, that means annually you receive approximately 490 kilogram per meter square per annum. That is how snowfall takes place. If you go into the Antarctica, it takes it is that firm to ice depth is approximately 95 meters, and it takes 2,500 uh, years to convert snow into the ice. Remember one thing, how long it takes? 2,500 years. But accumulation rate is just 22 kilogram, and the temperature is minimum minus 57 degrees Celsius. And if it goes to the Iceland, it is a 20 to 30 meter and age is approximately within 10 years. So you can see here that how long it takes. Key question is why it takes such a long time to convert a snow into ice, which is a 2,500 years in Antarctica, and it just takes the 10 years to convert into snow into ice in the Iceland. And it might be around 10 years in Himalayas too, even though there is no systematic data for us to do that. But Iceland is also temperate glaciers like what is Himalaya, even though it is a little bit towards the polar side. Ours is slightly, but both are in mid-latitude region. So you can see that it is. So think about it, and if you can find answer for this, I have given answer for you. Look answer in a certain way, that what I have explained to you earlier, that like in order to convert snow into ice, it goes through the process of metamorphism. It means it needs, either it can take the wet metamorphism, or it can take the dry metamorphism, or it also needs the compaction. So it has to meet three conditions, and and depending upon that, snow gets converted into ice. So you can now, from these three principles I have explained to you, you can really uh, argue with yourself to find out why it takes 100 years in Greenland, why it takes 2,500 years in Antarctica, and 10 years in Iceland. Okay, I will not answer that question. I will leave you to, and if you find it difficult to do that, maybe we can discuss that little bit tomorrow. So until now, we were talking about the physical characteristics of snow and ice. Now, key question is how we are going to find out these characteristics by using remote sensing technique. We know that snow changes, its grain size changes, its compaction changes, and we want to know that how it is going to change. So in this particular discussion, we will try and stick to ourselves to the visible and near infrared band of electromagnetic spectrum. Even though electromagnetic spectrum is wide and it is starting from gamma rays to X-rays to ultraviolet rays, and then there's a visible part of spectrum, then there's infrared, microwave, and radio wave. So many of these have been successfully used to estimate the characteristic of snow, including gamma rays, which is used because it is a passive microwave sensor. So it is extensively used in North America, which has very land mass. You have a background gamma ray radiation, then there is a snowpack, then it attenuates gamma ray radiation, so you can fly the gamma ray meter and then measure the attenuation and estimates the water equivalent. This is one of the technique which is extensively used, but gamma rays are very high frequencies, therefore you cannot use as an active sensor, but this can be used as a passive sensor, and that is what yesterday Professor Jay Srinivasan was talking about. Then there are microwaves are extensively used, and the radio waves are also extensively used to estimate the estimate the depth of glaciers, which is a ground penetrating radar. We will visit that some other time. So today we shall talk about the visible part of spectrum, which is which has a very frequencies into various, which is in blue, green, red of electromagnetic spectrum, and then we will talk about the near infrared and shortwave infrared also radiation in order to do that. Yesterday you have seen that these are the various platforms of collecting the remote sensing information. Sometimes you can use the ground platform, you can use low altitude aeroplane, high altitude, then you can use the low altitude satellites and geostationary satellites. So all kinds of sensors you can use. But before going into the uh, key parameters which determines how snow looks like on satellite images, it is important because we are talking about the visible and near infrared part of electromagnetic spectrum, and visible is a spectrum blue, green, and red. That is a spectrum where our eyes are sensitive. Therefore, how it looks like, you can look into that. One hand, we have water, you have a land, and you have a snow. Here, so they look quite different, and obviously they will have a different reflectance characteristics. And what are their characteristics? We will try and look into that. So in a visible part of spectrum, mm, the reflectance of snow, you can see this is snow, is very high. This is between 300 to 750, 850. This is a part which is visible, and 700, 850 you can see in that band is around is between blue, green, and red and near infrared band, which has very high reflectance. But the peak of reflectance you can see is which is around 550 nanometer. Is You have a peak of the reflectance. So around 550 there is a peak of reflectance. So before that it is slightly less. But overall, if you look into the visible part of spectrum, which is this spectrum, which has very high reflectance. As we go towards the higher wavelength, um, uh, that is where the reflectors start reducing, and it continues reducing till 1300 nanometer, and around 1350 it becomes very low till 1800, and subsequently it becomes a very low reflectance after 1350 nanometer. If you look in terms of other land feature, if you look because wherever there is a snow and glaciers, predominantly other land feature is the soil. So if you can look into the soil, here you can see this is a soil. You can see this brown color soil, and soil has very low reflectance when it comes to the visible part of electromagnetic spectrum. You can see here, this is very low reflectance. It is around zero point 0.1, and wherever snow has around 0.9 reflectance, and this is low reflectance. As you go towards the higher wavelength, its reflectance keep on increasing. And when it comes to 1350 to 1550 or 1550 to 1750 nanometers, which is a sphere, which is a shortwave infrared region, the reflectance of soil is very high compared to the reflectance of snow. So what it means is that in visible part of spectrum, you have a snow high reflectance, and sphere part of spectrum, you have a snow which is low reflectance, and this relationship is exactly reversed when it comes to the soil. You can see the another land feature, important land feature, is the vegetation. And you can see here vegetation, which is in greenish color. Uh, so um, what really, uh, what is here, you can see here is how reflectance is low in a visible part of spectrum. You have a little bit peak here coming near green, but still it is substantially low. And then you have a red edge over here, and then it has a near infrared radiation, which is very high. So it is still low. It is quite low compared to the snow in visible and near infrared. And it comes to the sphere part of spectrum, you can see the vegetation has relatively higher reflectance than the um, uh, than the um, than the snow. So this is very important for us to understand that. And another important question is, what is the reflectance of ice? So what happens is the reflectance curve doesn't change as snow gets converted into ice. Here you can see the dark blue, which is the snow, and light blue, which is the ice. Ice is reflectance, but the magnitude of reflectance reduces. Even the curve remains the same, and its relative characteristic doesn't change. What it means is that it has high reflectance visible range, and it has low reflectance in a sphere band. So this is how the characteristic of snow changes. And when we go into the snow cover monitoring by using the visible and near infrared band, which is quite often available, we will use this physical characteristic of snow quite significantly. We will dwell further on that. But why is like that? So what is the optical properties? So if you of snow and ice, which makes snow has visible part very high. As it gets converted into ice, its reflectance is low, and other characteristic of land features is different. So what really happens? So that any reflectance of object is fundamentally depends upon because of the refractive indexes. And you know that many of you are aware that there are two refractive indexes. One is the imaginary part of refractive indexes, and one is the real part refractive indexes. So optical property of ice is visible and near infrared wavelength, which is generally, if it is uh, optical property of ice, visible and is absorption coefficient. And uh, if you can really see here is imaginary part of refractive index, you can see here that it is very low. It means 10 raised to minus uh, 10 imaginary part of refractive index to 10 raised to power minus 2. So it is very small. That imaginary part of refractive index is very small, but its magnitude variation is very large. So it varies from zero point 0.4 to 2.5 wavelength. It is very 7 order of magnitude of so it changes minus 10, 10 raised to power minus 10, 10 raised to minus 2 or minus 3. So there's a significant amount of variation, but still it is very small. So spectral variation in real part, uh, part n is small, and difference between ice and water may not be significant. What it really means, it has a lot of meaning. That means the snow and water doesn't have a significant change in the refractive index, particularly the imaginary part of refractive index. That means it doesn't get absorbed. It doesn't absorb any incoming solar radiation, uh, and therefore you may not be able to separate between the snow and snow crystal and water crystal. That is the idea we are. And absorption coefficient K of ice and water is very similar, except region between 0.35 and point. So you can see here 0.3 in this part of electromagnetic spectrum. There is a minor variation, but it's really very small variation. And ice is slightly more absorbed there. So that's the idea. So visible spectrum K is very small and ice is transparent. If it is very small and ice is transparent, then why snow looks very white? That is the question. Because if you have any object, if you put a glass on any surface, if you put a glass on any table, and table has a black top, and you put glass on it, and when you look through it, it will look you black, isn't it? Because idea is it is very ice is transparent, and the K, which is the absorption coefficient, is very small. So it doesn't absorb any incoming solar radiation, and whatever incoming solar radiation is passing through as a transparent. So why it is white? That is a important question which we are going to address now, and that is because of interaction between the electromagnetic um, uh, radiation and ice crystal in a snowpack. What really happens is, as we have discussed, there is a ice or snow is aggregate of crystals, correct? And the in between that ice crystal there is air, and as there is air, once solar radiation comes through, if it is comes through in the contact with ice crystal, either it will go through it, it will get reflected back. Some of this will go through the ice crystal, and as it goes through the ice crystal, it will change its direction. Uh, it will change its, instead of coming this way, it will change its direction. As it comes out, there is again air in it. And when there is air in it, again it will change its direction. So what will happen is there is a multiple scattering will take place. And as snow, as there is more trapped air in between the ice crystal, there will be more opportunity for a diffraction will take place, and because of the change in direction and because of the forward scattering, snow will appear white. But as we start increasing density, as we remove the trapped air between the ice crystal, this opportunity for multiple scattering and forward scattering we are reducing, and mm, it reduces its reflectance. So as snow gets converted into the ice, the significant amount of opportunity for multiple scattering reduces, and then converts snow into ice because of the less air bubble, and its reflectance characteristic reduces, and its albedo is also reduced because of this thing. So it is important for us to understand why it is happening. Then there are different parts of the electromagnetic spectrum which is sensitive to the different characteristic of snowpack. So let us look in terms of the as snow, as we know that as snow go through the process of metamorphism, there are a couple of things happen to snowpack. And one of the key things happens to snowpack, we have seen there's a change in grain size. When the snow is in early phases, it is in dendritic pattern, we have seen, and as it passes through the dendritic pattern to the circular one, when it completely gets polycrystalline, there is a change in shape and there is a change in grain size. And which is an important characteristic of snow, because as it changes its sizes, it can potentially lead to the avalanches. So as we look into the grain size changes, as zero point zero 0.05 to zero point 0.2, zero point 0.5 to 1 millimeter, this is the radius of grain size, you can see that certain part of electromagnetic spectrum is not at all sensitive. So if you look into the visible part of electromagnetic spectrum, which is between the 0.4, 0.5, 0.6, and up to 0.7, they are not very sensitive to the change in grain size. But if you look into this part of electromagnetic spectrum, which is around 1100 nanometer, then there is a large difference can be found. That means if it has very high albedo when it reflectance when it comes to small grain size, and as the grain size increases, there is a reduction in the snow reflectance. There are also, remember this 1100 nanometer is a region of electromagnetic spectrum. From this data appears to be sensitive to grain size. And next we will see what happens is contamination. That means what really happens is as snow go through the process of melting, and then there is a lot of dust which is locally generated into the region, and wind blows it and it flows and it falls onto the snowpack. Then there are certain other anthropogenic activity can also create certain amount of contaminants on the snowpack, and its snow start melting. It happens like a filtering process, and it gets accumulated on the surface. So what happens in its effect is the maximum. We will look into this slide and see that what really happens here is, if you see that there's a small increase in soot, that means if grain size is approximately 100 micrometer, and it is changes from soot is changing from 0.5, you can see here that small increase in 0.01 parts per million by weight to 1 million parts per million, and is a 10 parts per million, and you can see that how change in reflectance will take place, and that change in reflectance is predominantly in this part of electromagnetic spectrum, which is 0.7, 0.9, the region which is sensitive to the grain size, which is around 1.1, is not significantly affected because of the contamination. So now we